So the solution is like this. So imagine x1, x2 plane like this with this droplet picture on it, and then transverse to that we have a z. Sorry, not z. This is y. This is y. There's the y direction perpendicular to this. So you have this three-dimensional space, and in this three-dimensional space, you have a three-dimensional space. And on top of this, over this three-dimensional space, you have three spheres. So you have S3 and S3 tilde, and the size of the S3s change as you move on the three-dimensional space, parameterized by x1, x2, and y. Sorry for the c. And the full metric is like this. Okay, and this and also in this three-dimensional space, you have some kind of Laplace equation, and this is defining this function z, and this function z goes to 1/2 if you are going to a point on this plane which is black. So you have this black region which is inside the droplet, and as you approach such a point, your z goes to 1/2. And if you go to a white region where z is -1/2, so you're approaching this y equals 0 plane onto a point where it's white, then z is going to -1/2, sorry. And you're given this boundary condition, you're solving some Laplace equation. So you have some smooth function z, and as you approach the x1, x2 plane, L11 plane, then you're going to 1/2 or -1/2, depending on where you are on the drawing. Okay, so some more words. So L11 diagram, it shows how these S3s shrink. Okay, I will tell you about this more later. And this describes smooth horizonless geometries. There is no horizon here. For example, this H is not vanishing, and there is no horizon. And this describes non-trivial topologies ordered by Flux. Okay, and these I will explain in coming slides. And so you have such a geometry for each droplet picture. So you have a one-to-one correspondence with some large n coherent state in CFT. Yes.
Is ADS 5 plus S5 a special example?
Yes, ADS 5 plus S5 is a special example where you have only one single black disk. Okay, so the full thing is like this. Okay, I just wrote it down for completeness. And okay, smoothness. So let me look at some smoothness in more detail. So as I said, you have some function z which is satisfying this Laplace equation, and this Laplace equation can be exclusively solved in terms of some integral over the y equals 0 planes, over this plane. So you have some propagator, and given some z on this plane, it's propagating to wherever you are. So in particular, consider the behavior of this function z near the y equals 0 plane. When z is +1, so you're approaching some point over here where z is +1/2. Okay, then the first term in this expansion, so if we are expanding, let's consider expanding this z in y, then the first term should be 1/2, because that's the boundary condition. But at the same time, you can see it explicitly, because if you're approaching this z, if you're approaching this plane, then it's like the this is an integral over the entire plane. But if you're really close to this plane, where the point is black, then it's like the entire plane is black, right? Because you can only see the point near u is contributing to this integral. So if you're really close to the point where it's black, then you can approximate this integral by replacing this z by simply 1/2, +1/2. then this is a simple integral that we can do, and it turns out to be simply pi over y squared, 2 pi squared, 2 y squared. Anyway, this turns out to be just 1/2. So this is the first term. And then the next term should be coming in powers of y squared, because everything is written in terms of y squared. And if you do, okay, and you're going to have some coefficient function depending on x. This is going to depend on the precise form of the droplet, but anyway, you have some function, positive function, c, and this should be positive because z must be between 1/2 and minus 1/2, because it's in some sense the average of the values on the z plane, sorry, y equals 0 plane. And if you are given this thing, then you can define, so okay, so you have now z, and z defines g here, and g defines h here, and they enter in the metric. So we can compute them. So e to the minus g, for example, can be easily computed to be proportional to y, and you have the c function, and h squared is like the c function itself. And then you can simply plug that thing, plug this into this y part and these sphere parts, so this one, and then you find that this is the asymptotic form, okay? And because this is a finite number, as you approach the y equals 0 plane, you have a sphere, which is sorry, what is it? So this is a 3 sphere, and this 3 sphere is shrinking because you have this coefficient y squared. So the f3 is shrinking, but it's shrinking in the right way, so that this part and this part combines to make a S4. So this is a smooth shrinking. And on the other hand, you have this other sphere. So this was S3 tilde, but you have S3, and this F3 remains finite because this is the radius, basically the radius squared, and it's finite. Okay, so as you approach this black point, S3 tilde, one S3 shrinks, but the other S3 is finite. Sorry, I said many things, but is it clear? Maybe I lost your look.
So c plus of x vanishes or behaves in a singular way at the boundary of the plan.
Right, that's what I'm going to turn to next. Yeah, so in two spheres, there are 2, 3 spheres. One shrinks and the other remains finite in the black region. But as you go near the boundary, the other finite sphere also shrinks.
Which coordinates correspond to the ADS 5?
It's a very complicated combination of all coordinates.
So it's hard to see.
It's hard to see in this one. You can see the S5 at least, and that's what we're going to see soon. So if you go consider the behavior near the black hole, black-white boundary like this, then, okay, in this case, let's consider this simple situation where everything is black in the upper half plane and everything is just white in the lower half plane. Then the integral is trivial, and you find that this is given by this. So this is a z function. And by extending, you see that this is plus minus 1/2 minus some function like this. From this, you read off that this function c is 1 over x2, basically. And because, as I said, this c function, 1 over c is the radius of the non-shrinking S3, actually, as you approach. So here, over here, the first S3 is shrinking, or S3 tilde is shrinking. But S3 is not shrinking, and the radius of that S3 is given by the inverse of this one. And the radius of that finite S3 goes to 0 as you go to the boundary. And you can see the same thing from the exact expression. So you have this part, and if you just plug in the exact thing, you get this thing. And okay, this part is fine. And if the first sphere is, okay, if you consider y equals to 0, then this and this one cancels. So as you approach the y equals 0 point, this figure shrinks, as I said. And on the other hand, you have the other S3. And as you approach y equals 0, the radius squared is 2x2 plus, sorry, 2x2. And that radius goes to 0 as you approach the boundary. Is it clear? Okay, so S3 tilde shrinks smoothly, and the other S3 remains finite, and on the black-white boundary, S3 shrinks. So, okay, so the picture is like this. S3 shrinks as one approaches the boundary from inside. So if you have a disk like this, then at each point inside you have some finite S3, but as you approach the boundary of this droplet, you get shrinking S3. So, and you have S3 over this disk D2, and that gives you S5. So, if you have many droplets, what you have is like some non-trivial cycles, five cycles, and you have some fluxes threading through those, and they're supporting the S5. This is a bit jumping ahead. But okay, so you can compute the flux through the S5, and you can show that it's proportional to the area of the black region. So the number of fluxes through such a droplet is simply the area divided by L Planck, basically. The Planck is GH to the 1/4 times S string. And one simple example is pure ADS5 plus S5. So this simple, this disk in the middle is the S5. And okay, as I said, you can compute the flux, and you can, well, this is the expression for the S5 flux, and you can compute the flux, and you can see that this is the area. Okay, I don't go through this. And okay, good. So how is the naive singular geometry recovered? I said that all these geometries are smooth, but in the end, the superstar geometry is singular. So how are these smooth geometries somehow representing the singular thing? The key is that the bubble area is quantized in terms of the Planck length. So as I said, the area is n times h, where h is the Planck length, basically, and it's gs times ls to the 4th. And when you take the classical limit, you have to take the classical limit, and that corresponds to sending L Planck to 0 and n infinity with fixed q, where q is defined to be this combination, which is just nh. So the area should be finite, but you're sending LP to 0 and to infinity. And what happens if you do that is that, okay, so when LP is finite and is finite, then you have this kind of black and white picture, droplet picture, and this represents a smooth geometry. But as you send L Planck to 0 and infinity to 0, keeping the area finite, then you get a finer and finer structure. All of this is still smooth. And in the end, when you have taken the limit, then this turns out to be a grayscale distribution. And this, if you plug in this grayscale distribution, so maybe z is like 0, maybe z is 1/4, something. Z is not plus half or minus half. Then this droplet gives you a singular solution, because as you have seen, here was some very non-trivial cancellation. For example, z had to start from 1/2, and then you have to have this y squared term, and to compute, when you compute g, you have this 1/2 minus z, and this is why you get y here. So if your z doesn't start with 1/2, then it's not going to cancel the thing, and the power in y is going to be really different, and your S3s don't shrink the right way. Okay, is this clear? And okay, but you may find it is a bit weird that we are talking about classical solutions and h, the Planck constant, at the same time. But it's not so strange, because LLM solutions are supposed to be should be regarded as the basis on which quantization is carried out. So you have solution space in gravity. Sorry. So normally you have phase space, and if you have phase space, then you can claim that your coordinates actually don't commute, and you can go to the quantum Hilbert space. So some area on your phase space is the Planck constant. And in gravity, actually the solution space is the phase space. So what we were talking about was actually the phase space. Maybe this is not very clear. Well, phase space is simply the space of solutions, right? Space of solutions. If you have this harmonic oscillator, this kind of rotating configuration is a solution, and a solution corresponds to a point in your phase space. So solution is the phase point. Sorry, not a point. A point in the phase space is a solution, and that's what is happening here. So if you are finding all possible solutions, solving the equations of motion of gravity, then that means that these are the points in the phase space.
So the solution space is not the space of all the solution, but this of the bubbling solution of this solution.
But these are all solutions in the 1/2 BPS sector.
Ah, okay.
Yeah, these are the full solution. Yes. So in some sense, each LLM solution is like this kx of a free particle. If you have a free particle, then what I'm saying is oh, sorry, this is not really right. This is not very good. Sorry, please ignore this part. Okay, but this is right. So this is like the classical orbit of an electron in old quantum theory. So if in old quantum theory, you think that there is a proton, and you have this electron going around, and classically it's just a circle, but that's not right, and you have to quantize, and you can see that quantization is such that your wavelength is somehow integer multiple of the the circumference should be the integral multiple of the wavelength of the electron. But still, it makes sense to talk about this round orbit because that's the basis of the quantization. So those LLM solutions itself are not real quantum state, but it's the basis on which to do quantization. So in that sense, talking about the Planck length and the Planck constant and the classical solution makes sense. Sorry, is this clear? I was not really clear. Okay, I can come back and ask a question. Yeah, and indeed, there is some work which really quantized the solution space in gravity, the LLM solutions, and reproduced the quantum Hilbert space of the free fermions on the boundary at large N.
Is there a Wigner interpretation of the quantum mechanics? So sometimes
Is
you
what?
a Wigner interpretation. So sometimes you talk about wave function on the phase space, and then the dimensional probability rule is slightly different. You can say psi of xp, but then the rules are. So that is something that has shown up before, not just in old quantum theory. So that.
I'm not familiar with the Wigner distribution. Sorry.
No, Wigner interpretation. So putting a wave function on the phase space.
What does that mean?
It's trying to give a more formal notion of what the thing you want to do, because you want to have a function defined by x and p. Yeah?
Yes.
So you're saying, well, x and p don't really commute, so I can't really talk about it. But there is a notion of putting a wave function on that. It's just the rules when you try to extract the rules are slightly different. Anyway, I was just asking if this has been done. This is not what these guys did in this one.
Yeah. Yeah, they really quantized this LLM solution by using Wigner cryptobits. Yeah, they just carried out the geometry quantization of the LLM solutions and found that the resulting turbulent space is the same as that of free turbulence on the body. No Wigner distribution or anything.
It's not the Wigner distribution, it's a different thing.
Wigner wave function.
Yeah.
Sorry. Maybe about the thing. Okay, some comments are in order. So generic states have large curve. So we said that you can consider such configuration. This is smooth and regular, horizonless. But if you compute the curvature of such a configuration, the curvature is really large because the curvature is like inversely proportional to the typical size of the droplet structure. So if you want to consider such a solution, higher derivative corrections are really important. So the LLM solutions are not really reliable. LLM solutions are solutions of two derivative gravity, and whether this is a reliable solution or not, it's really questionable. But we think that the higher derivative corrections are certainly important, but they should not change the qualitative picture. Namely, we must be able to describe the microstates in terms of the density of degrees of freedom of gravity. Namely, we don't have to consider massive straining modes to describe the real solution. The reason is that although these are really high curvature solutions, there's no singularity to be resolved. If you consider higher derivative corrections, then the solutions are going to be somehow deformed, but it's not like there is some really intrinsic singularity that should be resolved in the thing. So it's not going to, although you're going to change the solution, it's not going to change it qualitatively. It's going to be changed quantitatively, but not qualitatively. That's the intuition. So is it clear? Okay, so because of this, you trust the picture of the physics that you get from such fine structured droplets.
Well, I'm not sure about this picture. If
Okay.
you consider just classical mechanics with two derivatives, then of course the phase rate is just x and p. If you consider higher derivative theory, then you have x and x star and all the conjugate momentum
Okay.
to conjugate to the higher derivative.
Yes.
So why is that not here, applied here? If you have a high derivative gravity theory.
Okay, you have to be correcting the picture that I presented. By
Yeah, I mean, you mean high derivative without change the degree of freedom. I'm just thinking about this thing.
But is that what you're supposed to do in this perturbative string theory?
Yeah, I mean, if you do perturbative theory, of course, you just say perturbatively again. But it doesn't mean this picture is always correct. There's a limitation about the perturbative picture.
Yeah,
You
I
need to think
understand
about
that.
the true correct degree of freedom.
But I hope that's not the usual picture for this perturbative string theory, because perturbative string theory.
Just a different quantum field theory.
Yes.
If you have high derivative, sometimes you may change the phase space completely, and you have, for example, you have goals, and then you have to make sure that this high derivative correction doesn't really contribute a goals. I mean, otherwise this goals will, or this high derivative degree of freedom would be propagating, changing completely the structure of the field.
Well, okay, if that is true, then the way you include upper prime corrections to.
Or maybe you believe that any string correction will be okay, and keeping the same degree of freedom of the Einstein field.
Here you're assuming that there's half BPS solution.
It is happy, yes.
I think that's an important piece to the discussion.
Yeah.
Yeah, but that doesn't mean that you don't have any higher derivative correction.
No, they're high derivative, but they're BPS, so the spectrum is
So the point is that it'll still look like there's a bunch of stuff happening on the plane. So if you've gone to like the quarter BPS, I think you probably have to talk about two planes and so on.
Yeah.
It's a big mess.
Yes.
But I think it's the half BPS. You have so much supersymmetry, it's kind of always stuck with the.
It's for example, like central charge, for example.
Yeah.
Yeah, but I thought his point was that even so, you have to include higher derivative terms in gravity, and higher higher derivative means that you have not just Q dot, but so P. You don't just have P and Q, but you have Q dot, P dot. You
Yeah.
have to include.
But those higher derivative corrections are, if you just restrict in a half BPS sector, you're going to be tightly constrained, so.
Yeah.
But it's not like they're none, right? There are corrections.
Yeah, they're constrained, but then if they are so nicely constrained, then it doesn't change the dimension of the Hilbert space. If they're protected
Okay,
by.
variables can happen,
Huh?
but not in general, right? If you consider. I thought your question was.
Yeah, my question was general, but then I think it's right. If you are quarter BPS state, then they are. I mean, you have super algebra. You have super algebra with some central charge, and these things they give you a constraint protection on the Hilbert space.
I thought there was some argument that in string theory, you don't consider such new degrees of freedom even if you consider higher derivatives.
Mm-hmm.
Because otherwise you're going to change the spectrum of string theories, strings. You know the,
It could be a.
you know
if you
the,
take a general string background, of course we are not sure what will happen if you include all the string corrections.
so if you include all the string corrections, you
If
don't
you just
know
take
what.
a arbitrary bosonic background,
Yes,
even the tachyon could be removed by the tachyon condensation.
yes.
So if you just take any background without any supersymmetry, then of course we know nothing. But if your background is nice enough, then the correction are constrained, then I think people can say something.
It's
So
not
it is-
about the constraint. It's about the nature of perturbation. You're not. The perturbative expansion of string is not supposed to include more and more degrees of freedom. It's about just making the picture more precise. So I thought you start from the free string spectrum, and you're going to incorporate higher derivative corrections, but then it's not supposed to increase the degrees of freedom, right?
If your computation is reliable, yes. But if the background is not good enough, your classical solution is not good enough, then it could change or any statement you make from the classical analysis. I mean, just take cyber-Witten theory. I mean, the bound state, Taiwan and monopole, you cannot see from you can only see them non-perturbatively.
I don't. What I'm saying is not so special, right? So you just consider a string, a free string in free space, in flat space. Then you have the lowest mode and higher modes, and this is described as a field theory. You don't have just one field, but you have massless field, massive field, all these modes, and now you start to include higher derivative fractions. Then you don't have. Your field theory is now interacting and also have higher derivative corrections. So you don't have just phi dot, psi dot, but you have psi dot dot dot. Then does this mean that you have to increase the degrees of freedom to describe this field theory? That's not that's strange, right? Because string theory says that you have some string spectrum of the string, and that's it, and you can correct it by including interaction, but it's not like you have to double the degrees of freedom. So you're supposed to use the original degrees of freedom of the free theory and correct it by higher derivative fractions. So you have to treat the interaction as perturbative. And I don't see why this whole picture should change if you consider more general background.
I just want to say not all the string background can be used to do computation. Everything you say is correct if you are sure the background you start with is okay. But not all the classical background you get from Einstein gravity theory is a good background for doing string computation. It's just that. So I think we can leave it to other later to discuss.
Okay.